Good morning, everybody. Welcome back to non-Euclidean geometry. We're going to continue our discussion of incidence geometry today. We're going to start getting into some discussion of different models of geometry. I'll explain what that means here soon. Usual office hours, day after class, and at 2 o'clock. Tomorrow at 10 and at 1. As far as homework goes, yeah. Oh, you have a quiz on Monday on incidence geometry. Figure I want to have one extra day to talk about stuff before I give you the first incidence geometry quiz since we missed last Friday, which is why I'm moving this week's quiz to Monday. I will post a new homework set sometime between now and class on Friday. But my plan is to have a homework 3 on incidence geometry that'll be due on Friday next week. Speaking of homework, I believe you should have one for me. So if you could, go ahead and pass your homework forward, please. Oh my goodness. Alrighty, so where did they put mathematicians who commit crimes?
In prison.
In prison, so that they can be with all the other convicts.
It's been a couple years since I've gotten it.
Okay. Yes, it is. Anyways, quick refresher. We're looking at incidence geometry where we have these 3 undefined terms. I still have to define. Don't worry, we're going to give them some definitions today. Points, lines, and incidence. And these 3 axioms where for all points P not equal to Q, there exists a unique line L incident with P and Q. I feel like writing that all out in words, so I'm using a bunch of symbols, but it's Euclid's first postulate. Instance axiom 2. Every line has at least 2 points incident with it. There, freeze it down. I've got. Thank you. And instance axiom 3. Somewhere in space there exist 3 non-collinear points, P, Q, and R. 3 points where no line is incident with all 3 of them. And today, I want to. Well, let's say, last class we proved some propositions. We proved propositions 1, 3, and I encourage you all to take a look at proposition 5, which I think in the interest of time we're going to skip over for now. But once I post my packet solutions, I'll have my own proof for that proposition 2.5. And today, I want to finally give some definitions for these points, lines, and incidents, and see what exactly have you already proven about our definition of points, lines, and incidents, given what we did in class on Monday. So, here is what you've all been waiting for, our definition. Points. I'm going to define to be any one of 3 letters. A, B, and C. Those are your 3 points. They are the only points in all of existence. Lines. Any set containing exactly 2 points. And incidence. P is incident to L. And P is an element of the set L. Told you we're going to have some definitions that are a little different than what you might be used to. So, what's going to be an example of a line in this way of looking at geometry? What?
AB or BC.
Yeah, we could have the set containing the 2 points A and B. We could have the set containing the 2 points B and C. Are there any other lines? Okay.
The set containing the points AC.
Sets containing A and C. Brianna?
That was what I was gonna say.
Any others? I think that's it. So set, you've probably seen in another math class, but maybe you haven't seen a precise definition, which is good because precise definition of a set is actually horrifying. A set, you can just think of intuitively as just being a collection of objects. So these curly brackets are just sort of saying the outside lid to the set. And the things inside, in this case A and B, are just saying a set containing A and B. It's an object, think of it as being like a jar which A and B are trapped in. Those are our 3 lines. They are the only lines in all of existence. So, let's see. Brianna, describe for me a line that C is incident to.
Line L going through point C. Oh, AC would be incident line.
Yeah, I was gonna say, got 3 lines that you could potentially answer with. So you propose the second line, C is gonna be, yeah, I would agree. C is incident to this line. And the reason being, since C is an element of this set. This fancy looking symbol, by the way, that sort of looks like a euro, this is a mathematical symbol that just means is an element of. Is one of the things, in other words, inside of that set. So yeah, if these are our 3 lines, L1, L2, and L3, then we can certainly say that the point C is going to be incident to the line L2 because C happens to show up as an element in this set. Elaine, do you have a question?
No.
You did a little thing. Okay. Don't let it happen again.
Yes, sir.
Megan, give me any lines that C is not going to be incident to.
Line 1,
Why not?
because point C is not in that set.
Yeah, C is not going to be incident to L1, the set containing A and B, since C does not show up in that set. And to say is not an element of, we can have the is an element of symbol and then a little slash through it. And that's how our definition of points, lines, and instants is going to work. So we're actually going to call this a model. This set of definitions, we're going to give a specific name to. We're going to call it a model of instance geometry. And what it means for this set of definitions to be a model of instance geometry is it's basically going to be a way to define all of our undefined terms in a way that's going to make all of our axioms satisfied. Spoiler alert, instance axiom 1, 2, and 3 are all going to hold, which we'll look at on the next page. But in general, a model for instance geometry, or for any model of geometry, a model, for instance, is going to be a way to define all undefined terms will that will satisfy all of our axioms. So, depending on how you define your previously undefined terms, you could potentially have different models of a different form of geometry. For instance, this gives one model of instance geometry. I can give you another model. The way of thinking of points, lines, and instants that you're probably have been intuitively thinking about, where points are these dots in space, lines are these that goes between them. A point is instant to a line, if you know what I mean. That would give another way of defining points, lines, and instants that would give a different model of instance geometry. And it's going to turn out to be the case that this model of instance geometry will also satisfy all three of the instance axioms, and in doing so, is going to give us another way to look at and interpret the axioms of instance geometry. Any questions, comments, or concerns before we start looking at the three instance axioms and see how they apply in this situation? Yeah, right?
We just have to kind of assume that A, B, and C are not co-linear with them.
Well,
For that.
answer me this, Megan. Are there any lines that contain all three of A, B, and C?
So we can just define those as a line.
Yeah. Well, with this definition of lines, I would say A, B, and C can't possibly be, well, with this definition of lines and this definition of instance, I would say A, B, and C can't possibly be collinear because that would mean you have to have a set with three elements, which is not allowed by our definition. So let's go through it. Yes, Jack.
So were the definitions, like, it seems like Hilbert started with the axioms and then came up with definitions to fit those axioms, is that right? As opposed to coming up with axioms that seem to make sense of the definitions?
I would argue this. He came up with a set of basic axioms that he thought fit the definitions of kind of the more intuitive model of points, lines, and planes the way we're used to thinking about them. But once he came up with this set, but I would argue that's the model he had in mind, not this model. Once he came up with the instance axioms, then he started coming up with other models of, all right, what other ways can I define these sorts of mathematical objects in a way that will still satisfy these basic axioms that I want to be true? And this would be one model that he came up with for how can we define these terms in a way that will still satisfy the axioms. Does that answer your question?
Yeah.
Which came first, the model or the axioms? Classic chicken egg math problem. Well, you need definitions in order for the axioms to make any sense, but in order to have axioms, you have to have definitions to go off of. I would say that our intuitive understanding of points, lines came first, then the instance axioms Hilbert based around those, and then he came up with this model and some others that we're going to see that were based off of how else can we satisfy the instance axioms. So let's take a look-see. I'm going to look through each instance axiom and see if we can determine why that instance axiom is going to be true. Let's see. Nathan, for all points P not equal to Q, there exists a unique line incident with P and Q. Nathan, can you give me 2 points in our model? Doesn't matter which ones.
A and B.
Okay, A and B are your 2 points. Will, can you give me What is the unique line in our model that is incident with both of these points? Those are going to be incident with line 1. By the way, this symbol right here is a fancy way of saying incidents. So this is saying our incident 2 in this case. And only line 1. And I would also argue that given any pair of points, only one 2-element set contains them. If you were to give me A and B, I would say L1 is the unique line incident with both. If you were to give me A and C, L3 is the unique line incident with both. B and C, L2 is the unique line incident with both. So in other words, incidence axiom 1 is satisfied by this definition, by these definitions of points, lines, and incidents. It's satisfied in a very different sort of way than it is in our intuitive understanding of geometry, where I say, oh, here are 2 points, and here's the unique line that goes between them. We don't have any sort of picture like this anymore to go along with our understanding of instance axiom 1, but it is still going to hold true in the sense that you give me 2 letters, I can always give you a unique set that's going to contain those 2 letters. Specifically set that just has those 2 letters and nothing else. Let's take a look at instance axiom 2. Let's see. If I were to look at L2, does L2 have at least 2 points on it?
Yes. B and C.
How about L1?
Yes, A and B.
L3? That's all our lines. Hey, instance axiom 2 is satisfied. Every line is in fact incident with at least 2 points. In fact, in this case, exactly 2 points. But I would argue that L1, L2, and L3 are all incident with at least 2 points. Only 2 in this case, whereas with the traditional model, it's infinitely many points. But I would say in this case that any 2-element set has at least 2 elements. Would be a way that we could sort of interpret how instance axiom 2 holds in our model. And finally, let's see, Becca, instance axiom 3. Out of all of our points that you have to choose from, can you find 3 of them that are non-collinear, that doesn't have a line going through all 3?
Yes.
Which 3 points are you going to choose?
A, B, and C.
And you claim no line passes through all 3 of those points?
Yep.
Doesn't have them all, doesn't have them all, doesn't have them all. I just checked every line. I think you're right. Yeah. There exist 3 points. There exist 3 points, A, B, and C, which are not all contained in any line. Which are not all contained in any 2-element set. So in this case, just like with the traditional model, we can find 3 non-collinear points somewhere in our model. In this case, it just happens to be the case that those 3 points happen to be all of the points that we have to work with. But those 3 points, A, B, and C, out of the possible selection of A, B, and C, do happen to all be non-collinear, meaning instance axiom 3 is going to be satisfied. Yes?
Could we also say that it's satisfied because there is no 3-element set?
Sure. There is no 3-element set, therefore any possible selection of 3 points, even if we had more points to work with, would have to be non-collinear, and thus would satisfy instance axiom 3. Sure, that would be another way to basically write the same thing. Instance axiom 1 is satisfied. Instance axiom 2 is satisfied. Instance axiom 3 is satisfied. Thus, this set of definitions does in fact give us a model of instance geometry. You could say, write it over here. Since all 3 instance axioms are satisfied, this gives a model of instance geometry. If we had defined these slightly differently in a way that one or more of the instance axioms were to no longer hold, like let's say if I had the same set of points and lines, but I also added this as a line, so instance axiom 3 breaks, then this would no longer be a model of instance geometry because it doesn't satisfy the axioms, and therefore something has to break.
Would you still say it satisfies incidence geometry if it doesn't satisfy the definitions?
What do you mean doesn't satisfy the definitions? I'm sorry, I'm just not sure what you mean. Because typically, when you define a model, you're coming up with the definitions yourselves.
Mhm.
It's giving meaning to these terms which we had, but we never tried to define before. So the only definitions we really had before looking at a model is for terms like collinear, parallel, and concurrent. And those are really just definitions that give us shorthand ways of talking about things, because it's annoying to say these 3 points do not all satisfy a common, there does not exist a line for which these 3 points are all incident. It's a lot more annoying than trying to say these 3 points are not collinear. So really, when we talk about does a set of definitions give us a model or not, we're really just looking at, are these axioms all going to be satisfied? There are questions or comments? So we've looked at the instance axioms and interpreted each of them in our new model. I want to do the same thing now with the 3 propositions from Monday. The propositions that we kind of proved this class. See if we can interpret what these propositions are now saying. So let's start with proposition 2.1. If L and M are distinct lines that are non-parallel, then they have to have a unique point in common. Let's say, John, can you choose 2 of these lines for me?
L1 and L2.
L1 and L2. Okay, so these are going to be 2 distinct lines. Steph, do these 2 lines, L1 and L2, have a unique point in common? What's that? A. They have B in common and nothing else. So proposition 2.1 holds in this particular instant, and I would argue that any 2 lines that we choose that are not parallel to each other are going to behave similarly. L1 and L2, non-parallel lines, they only have a unique point, they have a unique point B in common. L1 and L3 have exactly A in common and nothing else. L2 and L3 have exactly C in common and nothing else. So I think we could actually write out proposition 2.1 in a unique way, given our new model, we can write it as two distinct intersecting two-element sets must only have one common element. How about proposition 2.3? For every line L, there's at least one point not lying on L. Emma, can you choose a line for me?
L2.
Okay, L2. Can you, Emma, give me at least one point that is not on L2?
A.
I think that works. B and C are in L2, but A isn't. So L2 is lacking at least one point. There's at least one point that is not incident to L2. And I think you can all probably guess the same is going to be true for L1 and L3. L1 lacks C, L3 lacks B. So we can rewrite proposition 2.3 in this model as saying any two-element set can't contain all three elements. Might feel like very much a duh, Dr. Hurstel, but that is something that kind of is saying how does proposition 2.3 relate to this particular model. And finally, proposition 2.5. Let's see, Katie, give me a point. Jacob, can you give me two lines, at least two lines that are incident with the point C?
L2, L3.
L2 and L3 will do the job. And in fact, I think, Katie, no matter what point you had chosen, she had chosen A. Jacob could have said L1 and L3 are incident with A. B, L1 and L2 are incident with B. And C, L2 and L3 are going to be incident with C. So, in other words, any element is in at least two element sets. So proposition 2.1, 2.3, and 2.5 turns out all still hold true for this particular model. But in a different sort of way than your intuition might have been thinking about the three propositions on Monday. All right, Elaine, I've got a tough question for you. Here's the clincher. Without actually having to go through and look at each of the three propositions, I already knew that propositions 2.1, 2.3, and 2.5 were going to hold for this particular model. And not just because I worked this out ahead of time because I'm the professor. Why did we know that this model of instance geometry is going to have to satisfy these three propositions?
Because those three propositions were already proved using the axioms, which we already showed fit with the model.
Exactly. We already showed back on this board that instance axioms 1, 2, and 3 hold for this particular model. What you all did on Monday is that you showed that if the three instance axioms are satisfied, then these three propositions must be true from just those axioms alone. Therefore, any model of incidence geometry is going to, any model, meaning any set of definitions in which the three instance axioms are satisfied, is going to have to satisfy these three propositions as well. So let's write that out. We can say that any model Incidence geometry. Must satisfy all these propositions since the propositions have to be true if the axioms are true. If the axiom holds. As per our work on Monday, where you all showed that propositions 2.1, 2.3, 2.5 have to hold true in any model of incidence geometry. Any questions or comments about that? So if we were to come up with a third model of incidence geometry, if we can show that these three axioms hold true in that model, under that set of definitions, then we would know without having to do any sort of further proof, these three propositions are going to hold true for that set of definitions. All right, in that case, I have an activity for y'all. If you look at the next page of the packet, actually, no, we're not at the activity yet. So, I have a question for you all. Let's say I'm going to try creating new models. Let's say we were to do the same set of definition for lines and incidents, except this time we're going to allow for 4 points. Meaning we have 4 letters, A, B, C, and D. So we'll call this one M1, where our points are going to be A, B, C, and D. Our lines are going to be any set with 2 elements. And incidence is defined the same way. Versus, let's call it M2, where our only letters are A and B. Our lines are going to be any set with 2 elements. And incidence is going to be defined the same way. Here's my challenge to you all. Go ahead and take a minute or two and see if you can decide whether for both of these, or for either of these, if either of these are going to give us a model of incidence geometry. As always, you're welcome to talk to your neighbors and see what they have to say. Actually, no. You know what? We're going to break you up into groups of 3 again. 3, 3, 3, 3. 1, 2, 3, and 2. Talk amongst your group members. Which of these are going to give, if either, are going to give us models of incidence geometry? I'll say that. You can hurt. You can do it.
I got lost. All right. Well, M2 is easy answer.
The first one,
Yeah,
I think it's the second one.
It's the only thing that like fixes.
For the four level.
So that is it also.
The two level.
Like,
Yeah.
For them
Yeah.
still, and then, there's, there is no freedom
So-
set.
All three axions are satisfied.
Because of the set, and we have two elements.
Say,
We have four.
There are 3 points.
Yeah.
we're immediately violating.
Yeah, so you do that
access.
first, and we don't have to do one or two, because it doesn't matter if we,
Exactly, so.
if those points are not all contained in any two elements set. They're all contained in one set.
Yeah, the only one
Sure do.
Great. Thank you.
Give your try, Joe.
You know what would work?
Yeah, I know.
If ordered water.
Oh, by the way, this,
If PQ was
So Dr.
QP.
Dr. Merkel's wife came by my office, and I'm looking for like a good two books.
No, okay,
I did.
Oh.
Because they put for their dog, they wanted more jokes.
Remember when I felt like I got this joke on free toilet?
Yes, I
Yeah,
remember.
yeah.
That was so
Yes, it was. Okay, let's come back together, because I think the groups, sounds like have come to a general consensus. So, Luke, Lacey, Joel, what were your all thoughts on this first model?
We thought it would hold because if it can hold with 3, all you're doing is adding 1 point. So you just have more lines, but everything else stays true.
Okay, given any unique points, does there exist a unique two-element set contained in it? I would agree. Does every two-element set have at least 2 elements? You betcha. Are there 3 non-collinear points? I think so. Joel, what were your group's 3 non-collinear points?
So if you have a line that's A and B, C would not be collinear, or D.
Gadzooks. So A, B, and C, or A, B, and D would work for your 3 points. In fact, I think any selection of 3 points would do the job here. So it's going to turn out to be the case that this is a model. Let's see. Nathan, Emma, Becca, what are your all thoughts on model number 2?
It doesn't go through
Why not?
because it breaks incident axiom number 3.
Why?
Because there are only 2 points in it, so 3 points don't even exist.
Gadzooks, we can't have 3 non-collinear points if we don't have 3 points? Yeah, I would say so. But instance axiom 1 is still going to hold. Given any 2 distinct points, say the only possible choice of A and B, I argue there exists a unique line width between them, i.e. the only line in this pseudo model. Does every line, i.e. the only line, have at least 2 points? Instance axiom 3 is not going to hold. This is not a model. Any questions or comments on this? Back on the joke. So, if you want to check if a set of definitions gives you a model or not, you basically have to go through the axioms and check off each one. And it's possible that some, but not all, are satisfied. 2 out of 3 ain't good enough here. In order to be a model, you have to satisfy of instance geometry. You have to satisfy all of the instance axioms. All right, let's take a look at our old friend now, the parallel postulate. So here I'm going to use the modern interpretation of the parallel postulate. Which is to say, given any line L in P not incident to L, there exists a unique line M passing through P parallel to L. So this is the modern version of Euclid's fifth postulate. My question is, we've seen three different models of incidence geometry. The traditional model, the three-point model, and now we've seen a four-point model. 3-point being just A, B, and C, 4-point being A, B, C, and D, this M1 over here. Here's my question to you. And I want you to continue discussing this with your group. Which of these three models does the parallel postulate hold true in, and which of the three models does it not hold true in, if any? So go ahead and take a couple more minutes and talk with your groups. See if you can determine in which of the three models that we've seen so far is the parallel postulate going to hold true? Yeah, traditional meaning Euclidean, except we're not really using Euclid's definition of points and lines. We're using your intuition.
Okay.
In terms of the definitions.
Wait for traditional.
Yeah, because if you're going to just find the axioms.
Right.
Like your traditional system, but you have the x axis, the regular definitions, you still know that 3 points are not incident to each other.
Yeah.
You know,
Yeah.
so there could be so
By traditional, I mean the Euclidean model of points, lines, and planes. So here's your points, here's a line that goes between them, that definition.
I think for 4-point it is possible.
Are we still working on just the three axioms though?
Alright.
There aren't even enough points, right, in line not exposed to the parallelism. Yeah, you also, if you look at line of 13 points, then there's guaranteed to be at least 2 non-stop on that line. And it's a parallel good, yeah. Oh, traditional and 4-point are both.
Have the traditional definitions of what a line is, but you're still in incidence geometry.
Oh, yeah, but Euclidean geometry. Yeah, but that would be better. It doesn't necessarily follow you. Right.
Yes?
How can we have traditional definitions in incidence geometry? Does traditional just mean Euclid's geometry?
Yeah, just Euclid, the way you're used to, your intuitive definition of points and lines, which I'm not going to write out on the board. A point is that which has no part, a line is that which has no breadth. Here are points, here's a line. Spoiler alert, I'm just going to go ahead and check this off so I can stop getting.
Yeah, because traditional Euclidean geometry contains postulate 5, so postulate 5 is true.
Properties of what we define.
And then for 3 it doesn't hold because you can check every case.
Intuitively, they're not.
Okay. Sounds like the groups are starting to quiet down a little bit. Group up here, what did you all think about the 3-point model? Okay,
No,
why not?
it doesn't work. Well, take your line L, which has 2 points.
Which points?
Let's
Concrete.
call them arbitrarily Q and Z.
Okay, your choices are A, B, and C.
Oh, okay. B and C. Oh, yeah, because it's any line, or every line, you can just disprove it for one, yeah. All right, and then pick a point not incident to that line. You
Okay?
only have one choice, which makes it really easy. A. Now, you can even go through and check all the lines that contain A and realize that they're all incident to line L because, or that a point in line A is incident to line L, so there's nothing parallel.
Gadzooks, there is no lines that are parallel to L.
Yeah.
The line with A and C intersects at C, the line with A and B intersects at B, that's all our lines. We can even say, no lines parallel to L at all. And so you produced a counterexample, Jared. So you claim that the Euclidean parallel postulate is no longer true?
That's right.
Everybody on board with that? I am too. We do not have the parallel postulate. Front corner. What are your thoughts on the 4-point model?
We think the 4-point model is good. We think the parallel postulate has full force.
Interesting. So if I were to give you an example of, say, Alex, give me a line.
A and B.
Give me a point out on that line.
B.
So front corner group. Yeah. Can you give me the unique line in this model that's going to pass through P and is parallel to L?
DC.
Gadzooks. I'm being a rebel by not going alphabetical order. But since order in a set doesn't matter, we could write it that way if you want. I would agree. The parallel postulate is in fact going to work in the 4-point model in all possible cases. Here's an example of one. Basically because if you take a line L, like there's always going to be exactly one line parallel to L, namely the line that contains the other two elements. And then any point that's not on your original line is automatically going to be on this new parallel line. So in the 4-point model, the parallel postulate holds true. So, what does this tell us about the relationship between the incidence axioms and the parallel postulate? Okay. Gadzooks. We have models where the parallel postulate does hold true. We also have models of instance geometry where it does not hold true. We're going to have a special term for that. Since there are models of instance geometry where the parallel postulate does hold, and ones where it doesn't hold, I'm going to say that the parallel postulate is going to be blank of the instance axioms. It's going to go in the blank lane.
Independent.
Yeah. It's going to be logically independent. This term we saw applied to the parallel postulate in Euclid's axioms before What this means is that you can neither prove nor disprove the parallel postulate using the instance axioms. Because if the instance axioms hold, it's possible for the instance axioms to hold and the parallel postulate to hold, like in the traditional and 4-point models, but it's also possible for the instance axioms to hold and for the parallel postulate to not be true, such as in the 3-point model, and therefore, that is how you can show logical independence here. The parallel postulate is logically independent of the instance axioms because it can neither be proven nor disproven using the axioms alone. And we'll leave it there for today. So when we come back on Friday, we're going to look at yet another model of the instance axioms, and we are going to talk about some notion called isomorphisms of different models. Have a good one.